Chapter 23. Computational Thinking and Problem Solving. Learning objectives. By the end of this chapter, you should be able to show understanding of how to model a complex system by only including essential details. Write a binary search algorithm to solve a particular problem. Show understanding of the conditions necessary for the use of a binary search. Show understanding of how the performance of a binary search varies according to the number of data items. Write algorithms to implement an insertion sort. Implement a bubble sort. Find an item in each of the following linked list, binary tree, hash table. Insert an item into each of the following stack, queue, linked list, binary tree, hash table. Delete an item from each of the following stack, queue, linked list. So from these things, these data structures like list, linked list, binary, a tree, hash table, stack, queue, from these things, how you add, delete, and update. Show understanding that performance of a sort routine may depend on the initial order of the data and the number of data items. Show understanding that different algorithms which perform the same task can be compared by using criteria such as time taken to complete the task and memory used. Show understanding that an abstract data type ADT is a collection of data and a set of operations on those data. Show understanding that data structures not available as built-in types in a particular programming language need to be constructed from those data structures which are built in within the language. Show how it is possible for ADTs to be implemented from another ADT. Describe the following ADTs and demonstrate how they can be implemented from appropriate built-in types or other ADTs: stack, queue, linked list, dictionary, binary tree. So there are so many structures, data structures for us to learn today. So many things. What is computational thinking? We have already been thinking computationally in chapters 11 to 15. Here is the formal definition. Computational thinking is a problem-solving process where a number of steps are taken in order to reach a solution, rather than relying on rote learning to draw conclusions without considering these conclusions. Rote learning is like memorizing to remember. So you can't say you can't just depend on that. You can't rely on remembering things when you do computational thinking. Every problem is a new problem. You don't get duplicate problems or repeated, or problems don't repeat. Every time it's a new problem. So for your exam also, remember you never get a question that you are familiar with. It always looks like it's something new that you have not learned. So that is why computational thinking is important. Computational thinking involves abstraction, decomposition, data modeling, pattern recognition, and algorithm design. So now you should remember the meanings of these things. Abstract, we have learned earlier, in earlier years, previous classes, you have learned abstraction, decomposition, data modeling, pattern recognition, and algorithm design. But here again, abstraction. It involves filtering out information that is not necessary to solve the problem. There are many examples in everyday life where abstraction is used. In chapter 11, we saw part of the underground map of London, UK. The purpose of this map is to help people plan their journey within London. The map does not show a geographical representation of the tracks of the underground train network, nor does it show the streets above ground. It shows the stations and which train lines connect the stations. In other words, the information that is not necessary when planning how to get from King's Cross Street and Cross to Westminster is filtered out. The essential information we need to be able to plan our role is clearly represented. So the route details are not necessary when you want to plan. Just the stations, they are enough. Abstraction gives us the power to deal with complexity. An algorithm is an abstraction of a process that takes inputs, executes a sequence of steps, and produces outputs. An abstract data type defines an abstract set of values and operations for manipulating those values. So, in simple terms, abstraction is filtering out information that is not necessary in order to solve the problem, to make the problem look clear for clarity. Then decomposition means breaking tasks down into smaller parts in order to explain a process more clearly. Decomposition is another word for stepwise refinement covered in chapter 12. This led us to structure programming using procedures and functions with parameters. So, standard example that we take for this is making a cup of tea is the main task. But if you break them down to smaller ones, you can have subtasks like boil water, brew tea, add sugar, and if you need, add milk. So that is like stepwise refinement. Step by step, you go down to details. Then comes data modeling. Data modeling involves analyzing and organizing data. In chapter 13, we met simple data types such as integer, character, and boolean. The string data type is a composite type, a sequence of characters. That means when the character means, like in Pascal, if you remember, only one character is allowed. The capacity is only one character. This data type won't allow more than one. But string is a combination of these, a sequence of characters. When we have groups of data items, we use one-dimensional, that is 1D arrays, to represent linear lists and two-dimensional arrays to represent tables or matrices. We store data in text files. In chapter 10, we use data modeling to design database tables. So for data modeling, we can use 1D array, 2D array, text files, and database tables. So if there's only just one column of items, you can use 1D array. More than one column, 2D arrays. and so on. Like we can set up abstract data types to model real world concepts such as records, queues, or stacks. When a programming language does not have such data types built in, we can define our own by building them from existing data types. There are more ways to build data models. In chapter 27, we cover object-oriented programming, where we build data models by defining classes. In chapter 29, we model data using facts and rules. In chapter 26, we cover random files. So there's a lot more to learn. Then comes pattern recognition. It means looking for patterns or common solutions to common problems and exploiting these to complete tasks in a more efficient and effective way. There are many standard algorithms to solve standard problems, such as insertion sort or binary search. Then pattern recognition in simple terms. If you are asked to fill in the blank in the series 1, 3, 5, and the last one, the next one, you can identify, you can recognize the pattern there and then answer that is 7. Likewise, you have a lot of similarities and differences where you can recognize in a problem. Then you can design the solution. Lastly, algorithm design. It involves developing step-by-step instructions to solve a problem. You all know that very well, the definition of an algorithm. Standard algorithms. Bubble sort. In chapter 11, we developed the algorithm for bubble sort. There was an example, 11.12, worked example. What were the essential features of a bubble sort? Refresh your memory about this. If you remember the meaning of this and you have the knowledge about it, then you know that the lighter elements go up, like the bubbles going in a liquid, bubbles going up. The lightest one or the smallest one on top in a series or in an array or any data structure. When you sort, the lighter ones go up and the heavier ones go down. Task 23.01, write program code for the most efficient bubble sort algorithm. Assume that the items to be sorted are stored in a 1D array with n elements. This is something you can do in Python when you are free. We have already learned these things. And then now we are coming to insertion sort. Insertion sort you can learn now. Imagine you have a number of cards with a different value printed on each card. How would you sort these cards into order of increasing value? You can consider the pile of cards as consisting of a sorted part and an unsorted part. Place the unsorted cards in a pile on the table. Okay, so unsorted cards, the whole thing. Place the unsorted cards in a pile on the table. You can picture it now. Keep the pack on the table, unsorted. Hold the stored sorted cards as a pack in your hand. Hold the sorted cards as a pack in your hand. So at the beginning, you don't have anything. To start with, only the first the top card is sorted. So you just take one card to your hand. The card on the top of the pile on the table is the next card to be inserted. Alright, can you picture it? There is a pack on the table. You take one card onto your hand and the next one on top of the pile is to be sorted. The last, that's the bottom card in your hand is the current card. So if you take the diagram, this out of this pack, sorted. So that's 47 you have taken into your hand. Next card, that is 6, that is on top of the pack, and all the others unsorted, like 54, all these things are unsorted. Then comes the next stage. So you take 6, the next unsorted, the next card on the pack is 6. Take it to your hand and then put it on top. Right? Because 47 is bigger, 6 is smaller. So 6 should be above 47. Then 54 is the next card. This becomes this next card. The brown colored one, next card, this. And the next stage is you take 54 into the hand, and 54, where should it go? Should go after 47 because it's bigger than 47. Then the 17 becomes the next card and it goes to the hand, then comes to the correct place after 6. And 93 comes there as the next card and goes down. That's the largest one so far. Then the final one is 28, comes to the hand and goes to where it belongs. So now it's sorted. 6, 17, 28, 47, 54, 93. The blue color thing is sorted. So that means it's in order. That's a very simple operation. And that is exactly what you do normally, no? Isn't it? When you have to sort the pack of cards, that is one good way of doing it. Repeat the following steps until all cards in the unsorted pile have been inserted into the correct position. Repeat until the cards to be inserted has been placed in its correct position. That is 1. Right? 1.1. Compare the current card with the card to be inserted. Now you will realize that what I explained earlier, looking at the diagram, is what is given here. If the card to be inserted is greater than the current card, insert it below the current card. Otherwise, if there is a card above the current card in your hand, make this your new current card. If there is no new current card, place the card to be inserted at the top of the sorted pile. That's exactly what we did earlier, and then you get the sorted list. What happens when you work through the sorted cards to find the correct position for the card to be inserted? That is, in other words, how do you find the place to insert? In effect, as you consider the cards in your hand, you move the current card down a position, just one place. If the value of the card to be inserted is smaller than the last card you considered, then the card is inserted at the top of the pile. That is position 1. If not, do another shifting. This method is known as an insertion sort. It is a standard sort method. So that's the thing we are learning now, insertion sort. You insert at the correct place. Whereas bubble sort, if you remember well, take a pair, compare, and then swap it. So that there will be more than one round of sorting. Sorting will be done again and again. The swapping will be done again and again until there are no more swaps. I hope you remember that. If not, you have to refer to it and then refresh your memory. This method is known as an insertion sort. It is standard sort method. We can write this algorithm using pseudocode. Assume the values to be sorted are stored in a 1D array list. So for pointer, this is the for and for loop we are using in pseudocode. Pointer equals to number of items. 2, the second one. The first one we already take, we already take it to the hand automatically, the first one. So from the next one only we have to do. Item, so number of items, if there are 10 items, it will become 10 here, 2 to 10. Item to be inserted equals list. List is the name of the array, 1D array list, and the pointer is in this case 2, the element, right? List 2, that's the item we are looking at now. List pointer means list because it's 2 now, pointer. Current item, another variable which is current item equals pointer minus 1. That is at this point, current item is 1, the first date item. Pointer to last item in sorted part of list, the last one that is sorted in your hand. Then another loop while list current item. List is the array name. In the list, the current item is like what we do here, 1 minus the pointer. If, while this is greater than item to be inserted. Item to be inserted is this. The next one rather. Next one to the current item. Because current item becomes this minus 1, pointer minus 1. So now we are referring to item to be inserted is the pointer number, that number, second element. So if you take the values, list current item is list 1. Item to be inserted is list 2. So in other words, while the first is greater than the second, and with that condition, there's another condition combining current item greater than 0. So current item greater than 0 means that it will be the first one or more, or greater than that, either the first or the greater one. List current item plus 1. So if this is true, if this condition is true, right? List current item plus 1. That is, in this case, it's 2. Current item is 1 and the current item plus 1 is 2, the next one, equals list current item. Can see what happens? If this is more than that, then they are like swapped. If this is greater than that, then list the two values are exchanged. Like if this is 45 and this list 2 is 30, then what happens? List 1 becomes 30 and list 2 becomes 45. The first two are sorted, small, big, like that it goes on. And wide. Current item equals current item minus 1. So you reduce 1 to get the to the top of it. Then after that, list current item plus 1. So the next, the third one equals item to be inserted. So the next one becomes current item. And it goes on. This also you have to do in Python and see for yourself. I'll be giving the answers, Python coding for this in separate files on the web page. On your course page, this will appear once you attempt, after you attempt it and submit. I will put it as assignments. Then task 23.02, dry run the insertion sort algorithm using a trace table. Assume the list consists of the following 6 items in the order given 53, 21, 60, 18, 42, 19. And write program code for the insertion sort algorithm. Assume that the items to be sorted are stored in a 1D array with n elements. So these have to be done. It's not difficult, it's easy. Once you start attempting, you will get the answers. If you just look at the question and wait, it will be difficult. Extension question 23.01. Investigate the performances of the insertion sort and the bubble sort by varying the initial order of the items. So you can take several different ordered lists. Same thing, different orders. Increasing the number of items to be sorted. That is also another good question. Exercise. Then we come to another one called binary search. In chapter 11, we developed the algorithm for a linear search. This is the only way we can systematically search an unordered list. However, if the list is ordered, then we can use a different technique. So the linear search is where an unsorted list, there is no order. And if you want to search for an item, then you have to do linear search, which means from one item to the other, one by one. We have to check each item and see whether you find the required item. Consider the following real-world example. If you want to look up a word in a dictionary, you are unlikely to start searching for the word from the beginning of the dictionary. Suppose you are looking for the word quicksort. You look at the middle entry of the dictionary approximately and find the word magnetic. Quicksort comes after magnetic. So you look in the second half of the dictionary. Again, you look at the entry in the middle of this second half of the dictionary approximately and find the word report. Quicksort comes before report. In the alphabet, Q is before R. So you look in the third quarter. You can keep looking at the middle entry of the part which must contain your word until you find the word. If the word does not exist in the dictionary, we will have no entries in the dictionary left to find the middle of. Middle of, then if you don't find the word, you will come to just one where there is no more middle. This method is known as a binary search. It is a standard method. Binary search because you divide into two. Divide the list into two, go on dividing by two or separating into two sections and finding which half it is. Let's look at the key term binary search. Repeated checking of the middle item in an ordered search list and discarding the half of the list which does not contain the search item. We can write this algorithm using pseudocode. Assume the values are sorted in ascending order and stored in a 1D array. List of size max items. So we have it in a 1D array named list. The name of the array is list. Size will be max items, the maximum number of items which are there. Found, that's like a flag. Found equals false. We initialize these variables. Search failed equals false. List, first equals 1. Last equals max items. Set boundaries of search area. So we have to provide the maximum number of items. While not found and not search failed. Search failed is false now. So this condition is true. Sorry, the search failed is this false, and not search failed means when this becomes true. Not found. Now at the moment is found is false. So not found is okay. Same thing. While not found means found is false, and search failed is not search failed is false. If you just say search failed, if you say while found, then found is true. But while not found means found is false. So this is correct. That condition is correct. And combined with and, search failed is true, but not search failed is false. So that is also correct. So this begins. Otherwise, this loop will not begin if these two are not initialized with false values. So what is happening in the loop? Middle. So we initialize a variable called middle equals first plus last. 1 plus, if it is 9 items, then it becomes 10. Divide by 2. Find middle of current search area. So if there are altogether 9 items, you add 1 plus 9, 10. 10 divided by 2 is 5. So 5 is the middle because there are 4 to the left of 5 and 4 to the right of 5, ending at 9. If list middle, now we have the list, the array, list middle, and middle is we have found is in this case, in this example I took, it will be 5. The fifth element equals search item. Then if this is the search item, like if you take the fifth item, if you find already the same, the item that you want, then found equals true. That is a lucky find. The very center of the list is what we want. Then it's true and then finish. None of these will happen. But else means the middle one is not the one that we are looking for. Then if first greater or equal to last, first is what? That is this 1. If 1 is greater or equal to last, no search area left. So if the last one is 1 here, then this condition is true. Or 1 or more. 1 if the first greater or equal to last one. Then search failed. That means not found. Search is failed. That means there are no more items. Else, if list of middle of the list, greater than search item, then that must be in the first half. Last equals middle minus 1. Move up a boundary. Don't worry, we'll do a sample and see. Else must be in the second half. First equals middle plus 1. That means move lower boundary. So let's take an example. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is our list, and this is the middle because 1 plus 9, 1 plus 9 equals 10, and 10 divided by 2 equals 5. So this becomes the middle. And our questions are: is first in this case is at the moment it's 1, no? If is first, no. What is the item that we want to find, right? Let's see, we want to find 7. 7 is the one we want to find. We are searching for this. So we find this at the beginning by checking the middle. Is the list middle is a search item. Search item. Search item is 7. And list middle. List middle is 5. No? The list, the element 5, element middle is 5. There are 4 here and 4 there. That's the middle element. So it is not what we want. Is 5 equals 7? That should be the question here when translated. Is like in your decision box, in your flowchart, is 5 equal to 7? No. So then this will not happen. Go to this. Else, if first is 1 greater or equal to last. What is last? Last is 9. This is first. This is last. Is first greater or equal to last? That means is 1 equal to 9 or greater than 9? No, isn't it? So this also will not happen. Then you go to this thing. If list middle, that is 5, greater than search item, is it? Is 5. Now you must have in your mind. Hereafter we won't look at this. We'll be keeping them in your head and we'll be doing. So middle is 5, last is 9. Is 5, this list middle is 5, greater than search item is 7. Search item is 7 here. Search item in red is 7. Is 5 greater than 7? No. So this will not happen. Only this will happen. Must be in the second half then. So we assume that it has to be. It has to be, not that is assumed. First equals middle plus 1. At the moment first is 1. So equals middle plus 1. Middle is how much? 5. Middle is fifth element. 5 plus 1 is 6. So first becomes 6. So now this first is gone. That upper half is ignored. We are taking from this half, from this onwards, and this is first. 6 becomes first. So we are going back. to this place. Not found. Still not found is false, and its search failed, false. It's not failed yet and not found yet. Middle equals first plus last divided by 2. Then what happens? A new middle we'll have to find. First is 6. 6 plus last is 9 equals 15. So 15 divided by 2 equals, say, we'll take it as 7, right? Not exactly 7, 7.5, but in this small, very simple operation, we'll take it as that. So the middle becomes 7. No? Earlier we found that the middle was 5. Now we find that the middle is 7. Let's look. Is 7, sorry, we calculated 7, middle became 7. So list middle is 7 equals search item. Search item is also 7. We have it in 7, red 7. Search item is also 7. So is 7 equals 7? Yes. Then found equals true. So we found this one. Found equals true, then nothing of this will happen. And when you go back, while not found, so it's false now. This condition is false because found became true. So since and condition, one of them becoming false, the whole thing will become false. While not found. So not found is not true now. It's found. Then you exit this loop. Again, we are checking if found equals true. Why is that? Because there are different ones. Because supposing if that item was not there, what we are looking for, that item was not there, then still found will be false. Satisfies here item not present in array. But if it is true, if found equals true, then that means found. Output middle. So in this case, middle is 7. The answer is 7 in this case. Output middle. Output position where item was found. So actually it's not 7 here. You must understand this is not 1, this is not 2. There are values in this. There are values, maybe words or numbers. Maybe student names, maybe student marks, vehicle numbers, any type of data. But these are the element numbers we considered. So if it was not found, then item not present in array. Okay. That is because you go on and on and on, and finally this you don't get this middle equals search item, you never get to it. So then you come out of this while the found having the value false what we put at the beginning. It has not changed. That means it's not there. Then task 23.03. Dry run the binary search algorithm using a trace table. Assume the list consists of the following 20 items in the order given. Let's look at the order. 7, 12, 19, 23, 27, 33, 37, 41, 45, 56, 59, 60, 62, 61. So that's all sorted. In this order, 20 items. Search for the value 60. How many times did you have to execute the while loop? Dry run the algorithm again. This time searching for the value 34, which is not there. Earlier, value 60 was there. And you had to answer how many times did you have to execute the while loop. To get into this, how many times did you divide by 2 and then selected the half. This time, try run the algorithm again. This time, searching for the value 34, which is not there. How many times did you have to execute the while loop? So you will find something interesting in that if you do it. Compare the binary search algorithm with the linear search algorithm. If the array contains n items, how many times on average do you need to test a value when using a binary search, and how many times on average do you need to test a value when using a linear search? Can you describe how the search time varies with increasing n? When the number increases, how does it change? 23.03 Abstract data types, ADT. An abstract data type is a collection of data. When we want to use an abstract data type, we need a set of basic operations. Create a new instance of the data structure. Find an element in the data structure. Insert a new element into the data structure. Delete an element from the data structure. Access all elements stored in the data structure in a systematic manner. So, ADT, abstract data type, is a collection of data. When we want to use an abstract data type, we need a set of basic operations. So these are the operations to be done on that. So abstract data type is a collection of data with associated operations. Collection of data with these operations. The remainder of this chapter describes the following ADTs: stack, queue, linked list, binary tree, hash table, and dictionary. How many? 1, 2, 3, 4, 5, 6. So 6 ADTs we are learning. It also demonstrates how they can be implemented from appropriate built-in types or other ADTs. How they can be implemented from appropriate built-in types or other ADTs. You already know the built-in types, which we have learned earlier from those, or an existing ADT. First, we'll take the stacks. So we are going in this order. The first one is stack. What are the features of a stack in the real world? To make a stack, we pile items on top of each other. The item that is accessible is the one on top of the stack. If we try to find an item in the stack and take it out, we are likely to cause the pile of items to collapse. Like, imagine, have you seen in hotels? Some hotels, some places where the meals are set, the plates are put in stack inside, or in the kitchen, maybe in the kitchen and inside a like a cylinder thing. So when you put something, one plate, and on top of that you put another plate, when you want to take out, you can take only the top one first. You can't find something at the bottom and uh, take it out, then it will all collapse. Figure 23.02 shows how we can represent a stack when we have added 4 items in this order: A, B, C, and D. First A, then B, C, D. Note that the slots are shown numbered from the bottom, as this is more intuitive. So this is the 1, 2, 3, 4, like that it goes on. There are 8 slots where you can put these, stack these items. You can stack one on top of the other. Stacking is like that. The base of stack pointer will always point to the first slot in the stack. So this is the base of stack pointer, always pointed to the first one. The top of stack pointer will point to the last element pushed onto the stack. It's called pushing, push into this. So the last item is the top of stack pointer. The top of stack pointer, yeah, the top of stack pointer will, when an element is removed from the stack, the top of stack pointer will decrease to point to the element now at the top of the stack. So for example, if the fourth element is taken out, if D is taken out, this will point at this third element C. That is how the stacks work. A very difficult thing. If you remember this stack of plates, where you can't take anything from down. This is like a cylinder and you put one by one. You can't put your hand inside this and down because it's covered. The plate is covering the space. So only up to this point you can put the hand, you can take that plate out. Something like that it happens. And the top of the stack becomes this. Next one is queues. What are the features of a queue in the real world? Think of queues. When people form a queue, they join the queue at the end. People leave the queue from the front of the queue. If it is an orderly queue, no one pushes in between and people don't leave the queue from any other position. So hopefully we should see these orderly queues everywhere we go. Unfortunately, it's not that. We don't see orderly queues everywhere, isn't it, in our real life? Never mind about that. Let's look at this now. Figure 23.03 shows how we can represent a queue when 5 items have joined the queue in this order A, B, C, D, E. So front of the queue is this. A became first. Now see here also A is first, but it's a 1, but base. It can't come out first. It comes out last. Here A came first and A goes first. This is the term used is first in, first out, F5, F4. In this case, first in, last out, F5, LO, FILO. Or you can also say last in, first out, LIFO, LI, last in, FO, first out. So that is just as a matter of information, but look at how this happens. So A, B, C, D, E, they are in this queue, front of queue pointer, end of queue pointer. So we know the beginning of the queue and the end of the queue so that people can join. People never join the queue at this point. They join the queue at this point. So same way here, base of stack pointer you can't reach. You can only reach the top of stack pointer. So anything adding has to come here, but going out also from there. Same place. When the item at the front of the queue leaves, we need to move all the other items one slot forward. That's how it happens. So when the first one moves away after paying, let's say at a cashier supermarket, a checkout, you pay, A pays and then A goes out. Then B must go there, C, D, E. Same way like at the doctors, the surgery or dispensary, patients, the waiting list are there. The first one moves, then all the others move. This would involve a lot of moving of data. A more efficient way to make use of the slots is the concept of a circular queue. Pointers show where the front and end of the queue are. Pointers show where the front and end of the queue are. Eventually, the queue will wrap around to the beginning. So like a circular thing goes like this round. Eventually, the queue will wrap around to the beginning. Figure 23.04 shows a circular queue after 11 items have joined and 5 items have left the queue. So look at it. How does it happen? The slot numbers are 1, 2, 3, 4, 5, 6 as usual. And J. So this is end of queue pointer. This is front of queue pointer. So this will go, F will go first, no? F will go first and this will be the next. And this is like after H only I. It's like an alphabetical thing in now A, B, C, D, E, F, G, F, G, H, I, J, K. Like that, wrap around. You know about wrap around, going from this end to that end. So that this will be like this. Just move this one there and this one here. So that you don't have to move everything like this. You don't have to move all the rest of it up. Here you just make the point different, right? Then linked lists. You get the linked lists. In chapter 11, we used an array as a linear list. In a linear list, the list items are stored in consecutive locations. This is not always appropriate. Another method is to store an individual list item in whatever location is available and link the individual item into an ordered sequence using pointers. An element of a list is called a node. So these elements here we are calling them elements. Now here in this linked list it's called a node. A node can consist of several data items and a pointer, which is a variable that stores the address of the node it points to. So it has a pointer like this. These are pointers, and then the data inside that. The node can consist of several data items and a pointer, which is a variable that stores the address of the node it points to. So it can vary, but at the moment it shows where it is pointing. A pointer that does not point at anything is called a null pointer. Null pointer. It does not point at any node. It is usually represented by this sign. A variable that stores the address of the first element is called a start pointer. That is how the linked list is defined. So look at this again, the node, an element of a list. So these are nodes here. In this case, there are 3 nodes here. Pointer, a variable that stores the address of the node it points to. So this is a start pointer. Pointer is the address. Start pointer addressing this to this one and this one to that. So it has the address of the next one. Conceptual diagram of a linked list. That is how this is done. And this is null pointer. We learned that null pointer, a pointer that does not point to anything, and it is represented by this. So here is a null pointer. That is, there is nothing else beyond that, which means that's a last node. Start pointer, a variable that stores the address of the first element of a linked list. So the first node, there is no node here. There is just a pointer here at the beginning of the linked list, just a pointer pointing to the first node. Opposite of that is in the last node, there is a null pointer, which means that it's not pointing at any other thing because it's the last one. A new node A is inserted at the beginning of the list. The content of start pointer is copied into the new node's pointer field, and start pointer is set to point to the new node A. Look at it again. We have B, D and L, right? B, D and L. For convenience, I'm going to take that screenshot into into a Word document and keep it side by side for easy reference. Cropping it. Then you can make it bigger. A new node A is inserted. So then what happens? Start pointer was there. Then B, D and L. B, D, L were there with a null pointer. Make it still smaller so that we have everything. Right. Then a new node A is inserted at the beginning of the list. How does it happen? The content of start pointer is copied into the new node's pointer field. That is, the start pointer is this. That point is copied to this one. The content of start pointer, earlier it would have been the address of B, no? Address of B. Now it's copied to this. And new node's pointer and new node's pointer field, and start pointer is set to point to the new node A. So start pointer is coming here, and the address of now what was here comes here, right? Let's say, for example, we'll take these as the addresses. Earlier, the start pointer had the address B. Now it changes to A, and the pointer of A points to B. Is that clear? We have the thing here. We'll see that we have the A here. Bring the A node here, then break this link from there and connect it to this. Break the address there and change that address to A's address. And then from A to B, have this as the A addressing A pointer to B. That is how it happens. Then in figure 23.07, that is this one, a new node P is inserted at the end of the list. Let's see when what happens then. The pointer field of node L points to the new node P. So that null pointer which was there, now it points to P, like taking, like connecting, that have you seen connecting train compartments, breaking the link and putting it here, then connecting it here, then this goes in between the start pointer and B. Here also it's not going inside, but it's adding to the end. So this start, the null pointer is put to the P, the pointer of P, whereas this will point to P, the new node. Earlier it was not pointing at anything, so we add the address of P there, so that it will point to P. And the last, the pointer of P becomes null pointer. Then only it will be added to the end. To delete the first node in the list, we copy the pointer field of the node to be deleted into start pointer. Copy the pointer field of the node to be deleted into start pointer. So what is to be deleted? B. We want to delete this one, so we bypass that. Instead of pointing to this, break this, remove the link from here and take it and put it to this one here. So start pointer is pointing at D. D is pointing at L. B, it's deleted, it's ignored. B loses its place in this list. Okay, the linked list. So the link is broken here. That is why it's called linked list. They are all linked from one to the other. So here the link is broken and a new link is brought here, connecting the start pointer to D. What do you do to delete the last node in the list? I think already you know the answer now. Now it's very clear. The pattern. This is what you call pattern recognition. If you know the pattern for one thing, then you can apply it to another. So what do? We set the pointer field for the previous node to the null pointer, so that this will be ignored, because the null pointer means it's not pointing at anything. It just breaks off and no connection to this anywhere. So where early it was here, the connection is broken and this null point is taken there, so that becomes the end. Sometimes the nodes are linked together in order of key field value to produce an ordered linked list. This means a new node may need to be inserted or deleted from between two existing nodes. So that's when you talk about an ordered list. To insert a new node C between existing nodes B and D, we copy the pointer field of node B into the pointer field of the new node C. We change the pointer field of node B to point to the new node C. So if you can picture this well, you can write your programs also accordingly and very easily. So see, what do you want to do? Insert a new node C between B and D. Between these two, you have to insert this C. So just break the link there like a chain. Imagine that there's a chain linking these two. Break it here, bring it and connect it to this one. So that now B is pointing at C. Earlier B was pointing at D. Now with this new connection here, B is pointing at C and then C's pointer pointing at D. So automatically this will be inserted here. To delete a node D within the list, that is in between something, we copy the pointer field of the node to be deleted D into the pointer field of node B. I think it must be very easy now for you all to think how to do it. Just break the link from here and bring it there to this. So that this will be ignored. We have already done it at the beginning and the end. So this is very easy now. Conceptual diagram of deleting a node within a linked list. So if you remember this concept like a picture, then your programming will be very easy. Because when programming, you don't see these things. You only type the coding, the real coding. But if you have this in your mind, back of your mind, if you have this picture, then it's easy to translate it into real code. Remember that in real applications, the data would consist of much more than a key field and one data item. This is why linked lists are preferable to linear lists. Linear lists are just one after the other. When list elements need reordering, only pointers need changing in a linked list. In a linear list, all data items would need to be moved. What does it mean? For example, now if you want to insert one here, you insert it then so that you have to move all the others to make way in a normal list, in a linear list. But in a linked list, you just adjust the link only so that this will be outside. It need not be like, though we see this in order like B, D, I, it need not be there. It can be anywhere outside. I mean, like physically, if you look at it, it need not go in between these two because this is the pointer will check. Even if this is somewhere there, somewhere away from this pointer will take it. The next, it will say that the next link is there. The next data node is there, so that the CPU knows. The computer will take that one, or the program will look at that. That is an advantage of linked list. Using linked lists saves time. However, we need more storage space for the pointer fields. So we need storage space for these pointers also. There are advantages as well as disadvantages. So the advantage is it saves time, but we need more storage to accommodate the pointer fields. In chapter 16, we looked at composite data types, in particular, the user-defined record type. We grouped together related data items into record data structures. To use a record variable, we first define a record type. We define the type, record type, and then give the data. Then we declare variables of that record type. So under that record type only, we'll give the variables. We can store the linked list in an array of records. One record represents a node and consists of the data and a pointer. When a node is inserted or deleted, only the pointers need to change. A pointer value is the array index of the node pointed to. So you are putting them into a different context, like putting into an array, but with the index pointing to the nodes. Unused nodes need to be easy to find. A suitable technique is to link the unused nodes to form another linked list, the free list. It's interesting, right? Figure 23.12 shows our linked list and its free list. Conceptual diagram of linked list and a free list. So this is the free list, which are not there, right? No data, they are deleted. A free list is like free items are there. We are not making use of that, but this is the one that we need, the real list. Start pointer be the normal thing. This is a free list. It says, let's look at the free list again, what it is. We can store the linked list in an array of records. One record represents a node and consists of the data and a pointer. When a node is inserted or deleted, only the pointers need to change. A pointer value is the array index of the node pointed to. Unused nodes. There can be nodes which are not used in our array. Need to be easy to find. A suitable technique is to link the unused nodes to form another linked list. That is called the free list. Okay, now you understand that. When an array of nodes is first initialized to work as a linked list, the linked list will be empty. So the start pointer will be the null pointer. All right. So the start pointer is the null in a null pointer. So the start pointer will be the null pointer. All where when an array of nodes is first initialized to work as a linked list, the linked list will be empty. Okay, the linked list is empty. Linked list is empty, and that is like this. No, there are nothing connected. Start pointer is null. Usually the end is the null pointer. So the start pointer will be the null pointer. All nodes need to be linked to form the free list. All nodes need to be linked to form the free list. Figure 23.13 shows an example of an implementation of a linked list before any data is inserted into it. So data is not inserted yet. Start pointer null, free list pointer is 1, that is this one. These are unused. The free list pointer 1 is this. We now code the basic operations discussed using the conceptual diagrams in figure 23.05, was the earlier one, to 23.12. Create a new linked list. So there's a comment at the beginning. This is to create a new linked list. Null pointer should be set to -1 if using array element with index 0. Right? Because some languages, the array element, the index is 0, the beginning. Constant null pointer equals 0. So we are declaring a constant in a name called null pointer equals 0. Declare record type to store data and pointer. Declare record type to store data and pointer. What is the data? What is the type we declare? List node. The name of the type is list node. A new data type, user defined data type. And declare data, that is string. Declare pointer, integer. So in this type we have two types built in. One is called the data, that is string. Declare the next one is pointer, which is an integer. N type. Declare star pointer integer, start pointer integer, free list pointer integer. Declare list 1 to 7 of list node. So you declare an array called list with 7 elements of node, of list node, that is of this type. See, once you define, now instead of normally when we declare an array, we say of integer, of string, right? The data type we have it here. Now we are using list node, which is declared here. our own definition, right? And these two, start pointer and free list pointer as integers. Then the procedure, Initialize list. Initialize list is a procedure to initialize the list. Start pointer equals null pointer. Okay. Start pointer equals null pointer. Set start pointer. Free list pointer equals 1. Free list pointer, we make it 1. For index equals 1 to 6. For index equals 1 to 6. Right? Link all nodes to make free list. List index dot pointer equals index plus 1. So we have the array called list. We have declared that as an array of this type, and the index, like the current index, becomes the earlier index plus 1, like incrementing the pointer of this index. The pointer, this one is there. We have defined pointer as an integer within this data type. That becomes increased by 1. Then n4. So everything is done. Index equals 1 to 6 means that index, first one is 1, becomes 2. Next time 2 becomes 3. Like that, it becomes like that. So list 7 pointer, the last one, becomes a null pointer. The last one we have to set, otherwise it will become connected to another one. So the last one we have to set as null pointer. Last node of free list. So separately we have to do this. This will do up to 6. List 7 dot pointer equals null pointer. So we give a null pointer for that. Then end procedure. That's it. This is how it is done to create a new linked list. Then you get insert a new node into an ordered linked list. Find an element in an ordered linked list. The operations, right? With what we discussed earlier. Find an element in an ordered linked list. Then delete a node from an ordered linked list. Access all nodes stored in the linked list. So those we will do programming. We will do in Python to implement these operations. Next time we will do that. In the meantime, on your own, you better try. You better try these things on your own, and doesn't matter if you fail. If you succeed, okay, then the real happiness is there. You are satisfied. It's a great thing. Otherwise, don't worry. But you have to attempt. If you don't attempt, and when I do it next time, you will see it as very easy. You will say, okay, it's very easy. That explanation is very clear. I can understand it. But at the exam, you will regret. So don't leave any room for regret. Do it now. Today itself, do without postponing. Time we'll be doing linked list. Linked list operations. We prepare for that. Okay. So let's meet again next time.